So today we're going to talk about Newton's method, but from an abstract point of view. So let me briefly review Newton's method itself. The idea is we're looking for the zero of some function f, right? And we want to find out some point where the function f is zero. And the way we do it is by forming a sequence of guesses. And each guess in the sequence is formed from the previous one by using this calculation here. What we do is we take the previous guess xn, we subtract off f of xn over f prime of xn, and that gives us the next guess. Okay, so we iterate this to get one guess after another, and then if things work out well, and they usually do, we'll end up with a pretty accurate approximation to the zero of the function f, right, where f is zero. Now, to formulate this in a more abstract way, what we'll do is we'll think of this thing here, this as a function which we apply at each step in order to get our next guess, right? So we define this function g of x equal to x minus f of x over f prime of x. And then what we can say is what we're doing here is at each step we're just applying the function g to the previous, our previous guess to get our new guess, right? So, if we are lucky enough to stumble upon the true value of the root, alpha, that we want, right, f of alpha equals 0, then since f of alpha will be 0, when we plug that in, we'll take alpha minus 0, and so g of alpha would just be equal to alpha. So, in this formulation, we can say is that the root we're looking for, the number we're looking for, is a fixed point of the function g. It's a point in which the output is the same as the input, so we call it a fixed point, right? And so, from the abstract point of view, we have a function g that we use to refine our guesses, right? At each step, we take our previous guess, apply g. We're looking for a fixed point, some point alpha where g of alpha is equal to alpha, and to find alpha, what we do is, or to estimate alpha, what we do is we keep applying the function g repeatedly to form a sequence of xn's, right? So xn plus 1 is equal to g of xn. And hopefully the sequence formed this way will in fact approach alpha. Now, the point of formulating it this way is that then we can apply the analysis we're about to do to any method of finding roots that can be fit into this framework, right? So there are a number of ways to find roots that work in essentially this way, where you have a guess, you apply a function to it to get a better guess, and then you repeat, right? Any method of root finding that uses that method can be formulated this way, and then we can apply the analysis we're going to do on the following slides. So, in this case, right, when we have an algorithm that works this way by applying g repeatedly to guesses to get better guesses, we'll get something called the Aiken error estimate. That's what I'm going to do on this slide. It tells you how the error actually changes over time with each iteration, at least when you're close to the actual root. Now, we're going to assume here, and I realize this may seem like an unfair assumption, but we're going to assume that xn does in fact approach the root that we want, alpha. Right? It approaches the fixed point alpha that we're looking for. Okay. Assuming that's true, then a conclusion we can draw is that if you look at the ratio g of xn over g of alpha over xn minus alpha, well, look, that's just the formula for slope, right? It's the average slope between the point alpha and the point xn. And so as xn approaches alpha, this is going to approach the derivative of g at that point alpha, right? So if we have a convergent sequence, right, the sequence is converging as we hope it will, then we can conclude that this ratio, g of xn minus g alpha over xn minus alpha, approaches g prime. Now, on the other hand, the numerator here, g of xn minus g alpha, well, that's equal to g of xn is going to be the next guess, xn plus 1, And since alpha, by assumption, is the fixed point, g of alpha is equal to alpha, then the numerator is just xn plus 1 minus alpha. So therefore, this ratio here is the same as xn plus 1 minus alpha over xn minus alpha, and that is exactly the ratio between the errors of these successive guesses, right? The numerator is the error in xn plus 1, and the denominator is the error in xn. So, because that ratio approaches g prime, what we can say is that for large n, right, when we've iterated a lot, we're confident that we're close to the correct value for alpha, then the ratio between successive errors is approximately g prime of alpha. Or rewriting this a little bit, you can write it this way, and we can say that the error in xn plus 1 is approximately g prime of alpha times the error in xn. Right? And hopefully, g prime of alpha is going to be less than 1, so that the error is getting smaller, right, as you iterate. Let's actually check that out in the case of Newton's method, right? So we'll calculate g prime of alpha in the case of Newton's method, where alpha is the root of the function that we're trying to find. So in Newton's method, g of x is x minus f of x over f prime of x. Take the derivative, right? So we get 1 minus, and we apply the quotient rule here, so we get this expression. Now we want to evaluate the derivative at the point alpha. So when you plug alpha in, it simplifies a bit because we're assuming that f of alpha is 0, right? Because we're assuming that alpha is a root of the function f, right? Is 0 of the function f. So that term disappears, and then what we get is simply a 1 minus f prime squared over f prime squared, so we get 0. 1 minus 1. So in the case of Newton's method, yes, this coefficient here, g prime of alpha, is much less than 1. In fact, it's 0. That's about the best you can do. So that's why Newton's method works pretty well, because when you get close to the root, then you're almost improving your error by an order of magnitude at each iteration, right? You're almost multiplying just by 0, right? So you're really radically decreasing the error at each iteration, right? Again, assuming that you're working for large n, right? So with Newton's method, we can say that for large n, the error in the estimate xn plus 1 is much less than the error in the estimate xn, right? The error goes down dramatically at each step. This leaves us with the problem of getting the value of g prime of alpha. There are two problems here. One of them is the very obvious problem that we don't know what alpha is. That is what we're trying to figure out, right? So we don't know what alpha to plug into g prime. That's not really such a fundamental problem, though, because if you manage to calculate g prime, then you can usually get a useful upper bound on what the magnitude of g prime of alpha could be, right? So we don't need the exact value. It'd be good enough to get an upper bound on how big that value could be. A more fundamental problem, in a way, is that g might be a complicated function. Remember that g basically describes the algorithm. It describes the algorithm by which you go from one guess to a better guess, right? In the case of Newton's method, that's a pretty simple algorithm, and therefore g has a simple formula, and it's easy to find the derivative. But you can imagine there might be more complicated algorithms that you'd use to refine your guess at each step, and then it might not be such a simple matter to calculate the derivative. It may even be that the function f, whose zeros you're trying to find, is a very complicated function. It's not easy to calculate its derivative, which you'd have to do in the course of computing g prime. So in cases like that, you're going to have to fall back on ways to estimate g prime numerically. Now, we will actually talk later about systematic ways to numerically estimate the derivative of a function. But for the moment, let's just work with what we've got here. Let's assume that we have this sequence of xn's, which is approaching the true fixed point alpha, right? So first of all, the xn's that we're currently looking at are pretty close to alpha, and also they're close to each other, right? If they're all close to alpha, then they're also close to each other. So then we can say that for large n, right, when xn is close to alpha, g prime of alpha should be pretty close to g prime evaluated at xn minus 1, right? So the previous guess should already be pretty close to alpha, and therefore g prime at the previous guess should be pretty close to g prime of alpha. Furthermore, the derivative at xn minus 1 can be approximated by looking at the change in g between xn minus 1 and a nearby point, like, for example, xn, right? So these are two nearby points, and therefore if we take the change in g over the change in x at those 2 points, that should be pretty close to the true derivative of g prime at xn minus 1. Now, g of xn is exactly xn plus 1, and g of xn minus 1 is xn, right? Because g is the function which we use to get our next guesses, right, to refine our guesses. And therefore we have this estimate: g prime of alpha is approximately equal to xn plus 1 minus xn over xn minus 1. In other words, the ratio of the changes in our estimates, right, for 3 successive estimates. So we denote this quantity by lambda n, right, and then we can use this lambda n to estimate what the derivative g prime of alpha is. So we can say, therefore, that the error in xn plus 1 is approximately equal to lambda n times the error in xn. Now, doing a little algebra on Aitken's error estimate with the estimate for the derivative g prime of alpha, right, which we're estimating using lambda n. Putting this all together, we can do some more algebra, and we can get what's called the Aitken extrapolation. So this is where we take our current best guess, xn plus 1, and then we put it together with lambda n and get an even better guess of what the true value of alpha is, right? So here what I've done is I've simply written out what the error is, right? Error in xn plus 1, that's by definition is just alpha minus xn plus 1. The error in xn is just alpha minus xn. And this is our estimate for g prime of alpha. So we got this approximate equation, right? The two sides are not exactly equal, they're approximately equal. Now we solve this approximate equation for alpha. Now remember, this is just a linear equation in alpha, right? We got alpha minus something equals something times alpha minus something. It's just a linear equation, so it's very easy to solve this for alpha. I'll leave that as an exercise for you, and what you come up with is that alpha is equal to xn plus 1 minus lambda n xn over 1 minus lambda n. So we could use this to get our an improved estimate for what alpha is, right? Rather than simply returning xn plus 1 at this point in the algorithm, what we could say is we'll return this Aitken extrapolation instead, right? Because this is an even better guess at what alpha is, right? Basically, the Aitken extrapolation is using the fact that we know we're a little bit off, and we know that our next guess is going to be a little bit off, and it tries to take into account all of those errors and come up with an estimate of what our answer would be if we could carry this process on for a much longer time, right? So that's kind of what the Aitken error estimate is doing. So we could use this formula. However, there's a slightly more convenient way to write this. So the rest of this slide, all I'm going to do is some junior high school algebra to rewrite this expression into something that's a little more palatable. So I'm going to introduce xn plus 1 minus xn plus 1. So in other words, I haven't changed the value of anything. I just added a term and subtracted it off. Then I'm going to put this over the same denominator, 1 minus lambda n, and combine these terms. And then we get a simplification, actually. So when I put this over the denominator 1 minus lambda n, I get minus xn plus 1 times 1, gives me this. And I get minus xn plus 1 times minus lambda n, so that gives me this, positive lambda n times xn plus 1, all over the denominator 1 minus lambda n together with the terms that were already in the numerator here. And now what we see is that these yellow terms disappear. I've got a negative xn plus 1 and a positive xn plus 1, so I can get rid of those. And all I'm left with are these two terms. And these two terms have a common factor of lambda n, which I pull out. So I pulled out that common factor of lambda n, and I wrote it over the denominator 1 minus lambda n. And what's left inside, after factoring out the lambda n, is xn plus 1 minus xn. So that's what I got here. And now when you look at this, what you can see is we've got the most recent guess for what alpha is, plus a kind of correction term. Right? So this is our estimate for what the correction is. And so rather than simply returning xn plus 1 as our best guess, we add the correction term in and we get an improved final guess for what alpha is. And this, again, is the way the Aitken extrapolation is normally used. So now I want to use this theory that we've developed about fixed point iteration to analyze the situation in Newton's method when f prime of alpha equals 0. So again, assuming alpha is the root that we're looking for, and if f prime of alpha equals 0, that can cause problems. Remember that in Newton's method, you have to divide by the derivative, right? You take x minus f of x over f prime of x. So you're dividing by the derivative. When x is close to alpha, and hopefully we do get close to alpha eventually, then f prime of x is going to be close to 0, and you're dividing by a number that's close to 0, that can have unbalancing effects, right? You're dividing by a small number, you can have underflow and overflow errors and stuff like that. But just more generally, it throws a monkey wrench into the works, right? So we want to analyze what's going to happen to the speed of convergence and to the rate at which the error decreases in that situation when f prime of alpha equals 0. Okay, so I'm going to, in a way, I'm doing a specific example. I'm going to assume that f is a function that looks like x minus alpha to the m, where m is some positive integer, times another function h of x, where h of alpha is non-zero, right? So this is a function that's designed to have multiple zeros at alpha, right? So not only is f of alpha equal to 0, but if m is bigger than 1, then the derivative of f will also be 0 at alpha. And basically, whatever m is, that'll tell you how many derivatives you can take and still get 0 at alpha. So, if we calculate f prime, we get this, right? And then if we calculate the function g, for Newton's method, it's going to be g of x equals x minus f of x, which is this guy, divided by the derivative, which is this guy, so you get this mess here. And now I'm going to do something, well, let me see. First of all, you get some cancellations, okay? So we can cancel m minus 1 factors of x minus a in the numerator and denominator. So it simplifies a bit. That's good. But now we're going to take the derivative and calculate g prime. Okay, so that means we have to apply the quotient rule to this mess. And it's rather hideous, so I wrote it all out here. But it's just applying the quotient rule, right, to a fraction. So it's basically just a Calc 1 exercise, although the algebra is hideous. The good thing is that we're only interested in g prime evaluated at alpha, and when you plug in alpha, you get a radical simplification because all of these terms that have x minus alpha are going to disappear, right? So all of those terms disappear, and all you're going to be left with is you're going to be left with a factor of h in the numerator times a factor of m times h, and in the denominator you're just going to have m times h squared. And you simplify that, the h's all cancel, and all it boils down to is g prime of alpha equals 1 minus 1 over m. Okay? So that's nice and simple, right? That's easy to work with. In fact, the derivative doesn't even depend on the particular nature of the function h, right? It only depends on m. Kind of interesting. On the other hand, this result is bad for what it tells us about g prime of alpha. Remember, by the way, what g prime of alpha represents. it came up in the Aitken error estimate. It tells us the ratio between the new error and the old error in our estimates for the root, right? And remember that in the case of Newton's method, if f prime is not equal to 0 at alpha, then we found out that the derivative g prime of alpha was equal to 0. And that was very good because it meant that the error is reducing very, very quickly. However, in this case, we're not getting 0 for g prime of alpha. We're getting 1 minus 1 over m. So, for example, in a case where f of alpha equals 0, as of course it should be because we're assuming alpha is a 0 of f, and f prime of alpha equals 0, then m would be at least equal to 2, right? And in that case, g prime of alpha would be 1/2. Now, that means the error is getting smaller at a rate of 1/2, right? Whatever the error is this time, it's about 1/2 of what the error was last time, right? Every time we iterate. That's not so bad, but it's certainly a big difference from the dramatic size reduction we saw when f prime of alpha was not equal to 0, and then we were getting some dramatic reductions in error. So, okay, so this makes a big difference in the speed at which Newton's method will converge. If f prime of alpha is equal to 0, you can expect an order of magnitude fall off in the speed of convergence to the root. Okay. The book suggests one possible way out of this. I think this is almost so unlikely to work very well, but nevertheless, it's an interesting approach. So what they say is, what you could do is you could estimate g prime of alpha from the xn, as we saw in the previous slides, right? You can estimate g prime of alpha using this method, right? By keeping track of your recent xn's, and then you can use that to get this estimate lambda n for g prime of alpha, right? So you can do that to estimate what g prime of alpha is. Then, when you've got an estimate of what g prime is, you can try to work backwards from that to figure out what m was, right? So you figure if g prime of alpha is approximately 0.75, then you figure that g prime of alpha is probably theoretically 0.75 or 3/4, which means m would be 4, right? So g prime of alpha would be 1 minus 1/4. So you make an educated guess of what m is, and then you kind of know what the form of f is. F looks like x minus alpha to the m, and you know what m is. Then what you can do is you can try differentiating this m minus 1 times so that you'll have just one factor of x minus alpha here, right? If you take this expression, differentiate it m minus 1 times, you'll only have one factor of x minus a left, x minus alpha left, and then furthermore, the next root, the mth root, will not be 0 at alpha, and therefore you return to the situation where you have rapid convergence. This m minus first derivative will have the same root alpha that your original function did, but its derivative, which will be the same thing as the mth derivative of the original function, will not be 0 at alpha, and therefore you can expect rapid convergence. So it may be that you get much better results if you replace f with the m minus first derivative of f and find the root of that. That seems a little far-fetched to me, but I can imagine in some situations it would actually work.